Hello and welcome to this Dr. Frost Maths video on vectors. We're going to be exploring some of these questions in a second, but before I do that, let's introduce the notion of what a vector is. Now, you should hopefully already be used to the idea of what a coordinate is. So if I had a coordinate of, say, 3, 1, coordinates represent a position in space, whereas a vector represents a movement in the space. So if I was to write a vector like this, 3, 1, now you always put the numbers on top of each other and do not write a line in the middle. This is not a fraction, it's a vector. What that means is that you're moving 3 along on the x-axis and 1 along on the y-axis. So if we were to start here, we move 3 along on the x-axis and 1 along on the y-axis, and that tells us the overall movement. So this here would be the vector. Now you may have seen these if you've done transformations before, because do you remember that to describe a translation you have to say how the shape has kind of shifted across, moved across, and you use a vector to describe that movement. So vectors describe movement, whereas coordinates describe a position, and you can see the different way in which they're written. Now there's different ways in which we might write vectors. We can write a vector in this way here, using this kind of bracket notation. But if we had, say, 2 points, so we had a point A and a point B, and by the way, we tend to use capital letters to represent points in space. Now, if I wanted to represent the movement from A to B, there's different ways I could write it. I could write it as a little letter, so we can actually use algebra, and we use lowercase letters for vectors. So we could say that A represents this particular vector, and we could say what A was. So I could say that A is equal to 3, 1, for example. So we can use variables to represent vectors, just like we can with normal numbers. And sometimes, by the way, I'm not particularly dictatorial about this, but some teachers insist on underlining the letter to say that it's a vector. Technically speaking, you should make the letter bold, and that's the sort of way you actually see on printed text. Another way of describing this vector is to say, well, we're moving from the point A to the point B. So I could also write this vector as AB with an arrow on top, and that is saying it's the vector from the point A to the point B. Now, just a few properties of vectors before I move on. Let's say we go back to this kind of vector A, which is 3, 1. So that's A. Now let's just say we did another vector. So let's say we moved at this point a vector B, which is, well, it's moving a bit along the x-axis, let's just say it's 4, but the y value is not changing, so this is 0. And just to sort of reiterate that, remember that the top value of the vector is the change in x, and the bottom value of the vector is the change in y. Yep. Now, could we write a vector to describe the movement from this initial point to this final point here? Now, if we look at the total x we've moved 3 along the x-axis here, then an additional 4 along the x-axis here. So in total, we've moved 7 along the x-axis. So we can actually write this as sort of adding the vectors. So if we were to move this vector and then this vector, we can add these together. So we've moved 7 along the x-axis in total. And what have we moved along the y-axis in total? So we can see the y value is increasing by 1. Let's move up by 1. And then the y value isn't changing at all. So the y value is still 1. So the point is that if we want to move a vector followed by another vector, we can just add the vectors together. And adding vectors is very easy because we can just add the x values, so 3 plus 4 is 7, and we can add the y value, so 1 plus 0 is 1. We can also scale vectors as well. So if I was to write 4a, for example, if this is a single a, then 4a would represent a second a, and then another a, and then another a. So that could be described as a single vector, which we write as 4a. And to work out 4a, you might be able to guess how this works, but all we do is we just scale each of the numbers in the vector by 4. So it'd be 4 times 3, 1. So we times the 3 by 4, which is 12, and we times the 1 by 4, which is 4. So whenever we scale a vector, and this, by the way, is known as a scalar. So a scalar is just a number which scales a vector. Then we multiply each of the numbers in the vector by that number. So just to summarise everything we've seen so far, vectors just represent a movement of something in space. The top number of the vector represents what x is changing by. The bottom number represents what the y value is changing by. And we can add vectors together to represent the combined movement of moving one vector followed by another vector. And we can also scale vectors. One last basic before we get into the questions. Let's just say I've got a diagram like this, where I've got a vector A and then a vector B like this. And this is the point A, this is the point B, and this is the point O. How could I describe the vector to get from A to B? Well, we want to find a path from A to B. And by the way, with vectors, it doesn't matter what path you go, as long as you end up in the correct place. So, if I want to get from A to B, I don't know what it is directly, but I could go this route, can't I? Now, what's this vector here? Well, it's the wrong way across this vector A. That's A. What would the opposite way be? Well, we actually say it's minus A. So if you go the wrong way across a vector, it's going to be negative. So it's going to be minus A. And then we are going the right way to get to B, so that's plus B. So we can write the vector like this. Now, minus A plus B, that's the same as B minus A, just like minus 3 plus 2 is the same as 2 minus 3. So that might make you think, well, if I'm starting from A and I want to get to B, I could first do a vector B. So notice, if that is B here, then if I did the movement from here instead, and by the way, it doesn't matter where the movement actually occurs, it'll be the same vector as long as you're moving in the same way. So whether I move like this or move like this, it's exactly the same movement. It's just I have a different starting location. So that would be a vector B as well. And then I'm doing a minus A. Well, I know that A is going that way, and that's a minus A. So from here, I'm doing minus A, and that would indeed get me to B. So you can see that that is the same as that, but represents a slightly different path, because that represents this path, whereas that represents this path. But as I said, as long as you end up in the same place, it will be the same vector. Right, that's enough of me rabbiting on, so let's do some of these questions. We've got A is 3, 1, and B is 0, minus 4. Determine A plus 2B. So A plus 2B would be equal to, if we write the vectors, we've got 3, 1 plus 2 lots of B. So 2 lots of 0 minus 4. Now remember, when we scale a vector using a scalar, we just times the top and bottom by the 2. So that's going to be 0 times 2, which is 0. Minus 4 times 2 is minus 8. And then we just add the numbers. 3 plus 0 is 3. 1 minus 8 is minus 7. And what about A minus B? So we've got A, which is 3, 1, minus B, which is 0 minus 4. So in the same kind of way, we subtract these numbers instead. 3 minus 0 is 3. And 1 minus minus 4, that would be 1 plus 4, which is 5. Question 2. A, B, and C have coordinates 3, 0, 5, 6, and minus 2, 0. Determine A to B, B to A, and A to C. It might help to just kind of approximately write where these points are. So let's say A, 3 zeros here. B has coordinates 5, 6, so that's slightly across and up. And then C is minus 2, 0. So C is somewhere over here. So C, minus 2, 0. Now we want to first work out the vector to get from A to B. So this vector here. So you just got to think, what movement are we doing to get from 3, 0 to 5, 6? Well, let's think about the change in x first. Well, the change in x to get from 3 to 5, well, the x value is going up by 2. So it's 2 there. And what's the change in y? To get from 0 to 6, the y value is going up by 6. And therefore, that vector from here to here is a change of 2, 6. What about B to A? Well, that's just the other way around. So that's going from B to A. So you can see to get from 5 to 3, the x value is going down by 2. And to get from 6 to 0, the y value is going down by 6. So we get that. So it's just the negation of that. And then finally, A to C. We want to get from A, which is 3, 0, to C, which is minus 2, 0. Now the x value is decreasing by 5, so it's minus 5. And the y value to get from 0 to 0 is not changing at all. So that is 0. Question 3, and then we get onto the interesting ones. A has the coordinates 3, 1, let's draw that. And A to B, so the movement to get from A, where we currently are, to B is 5 minus 2. So 5 minus 2, that's kind of moving 5 across and 2 down, because the y value is decreasing by 2. So it'll be like this. Determine the coordinates of B. Now all we need to do is just to start with a free one, and then this is telling us, this vector, what the x value is changing by and the y value is changing by. So we start with 3, and then the x value is increasing by 5. That means it's now at 8. And the y value is starting at 1, and then in this vector the y value is decreasing by 2. That's what this movement is doing. 1 minus 2 is minus 1. So we would end up here at 8 minus 1. Now question 4, the vector from O to A is little a, you can see on the diagram, and the vector from point O to point B is little b, so you can see the b there. M is the midpoint of AB. Determine in terms of little a and little b what is A to B. So if I just draw this out again, now we actually did this one earlier, didn't we, the first part. So to get from A to B, we don't know the direct route from here to here, but we know that we can go this way. So minus A, because we're going the wrong way, minus A plus B. So A to B we've already seen is minus A plus B, or if you prefer, B minus A. Now O to M is a bit more complicated, so I want to get from O to M. Now there's two different routes I can use to get from O to M. I could either go that way or I could go that way. So I'm just going to go this way here, like that. So let's think what we need to do to get from here to here via this route here. So we're first doing an A, yep. So we're doing an A. And then, once we're now at A, we're going halfway across the vector to get from A to B. So it's half of whatever A to B is. Now this is a bit weird because we seem to have a root within a root, and that's quite common with vectors. So just to reiterate, we're initially going in A to get from O to A, and now to get from A to M, we can see that's half of A to B. And then we need to separately work out what the root from A to B is, this root within a root. But we've already worked out what A to B actually is, so we can write A plus half of, in brackets, minus A plus B. And then this just works like normal algebra, so we can expand and simplify this expression. So it's A plus half times minus A, that's minus half A. And half times B, that's plus half B. Now if we've got one lot of A and we minus half a lot of A, 1 minus half is half, so it's half A, and then it's plus half B. And this sort of makes sense when you think about it. So if we're going from O to M, we can do half of A. So look, if I'm starting here, if I did half of A, that's half of this. So I go like this, half of A. And then I'm doing half of B. Now B is a vector like this, so half of B would be a movement like that, halfway across. So if I'm currently here, half of B would be a movement across like that. And we can see, look, that actually works. This does feel right. Now more questions involving more complicated fractions of vectors. C is a point on AB such that AC to CB is 2 to 1. So AC to CB is 2 to 1. So that's twice as big as that length there. Determine O to C, so from here to here, in terms of little a and little b. So if I just write this out again. Now when I get a ratio like this, like AC to CB is 2 to 1, I tend to write the ratio on the diagram just so I don't forget it and it's there for me to visually see. So we want to get from O to C. Now let's choose the appropriate path. Let's go this way around, doesn't really matter. So to get from O to C, we first go to A. So O to C, we're doing the 3A first. And then it's plus, now we're here, it's some fraction of A to B. Now what fraction of A to B is? Well, if you imagine that's, say, a length of 2, and that's a length of 1, that total length would be 3. So going across here would be 2/3 of the way, wouldn't it? So we're doing 2/3 of what? Well, it's 2/3 of A to B. So it's plus 2/3 of whatever the vector is from A to B. Now we've got another vector here, AB, so we separately have to work out this vector AB. So we separately have to work out this root within the root, which confuses a lot of students. So let's work that out next. A to B, well, if we're starting from A and going to B, then we're going to do minus 3A plus 12B. And because we know that separate vector, we can now substitute this expression into there. So we now know that O to C is equal to 3A plus 2/3 of A to B, which is minus 3A plus 12B. Then we expand and simplify. So 2/3 times minus 3A is minus 2A. 2/3 times 12B is plus 8B. And then we collect like terms. 3A minus 2A is A plus 8B. And again, we could get a sense of whether that feels like it works. So if we're starting from O, if we do an A first, that's 1/3 of this length. So that would be A there. And then we're doing 8B. So 8B is 2/3 of 12B. So that whole movement is 12B. So 8B would be like 2/3 of it like that. So if we're currently here, that would be an 8B. And we can see, look, that does indeed get us from O to C. So that feels right. Now question 6. O to A is A. So that's A there. O to B is B. So from here to here is B. D is the midpoint of AC, so D is the midpoint of AC there. And B is the midpoint of AC, so B is the midpoint of AC. Prove that O to A is parallel to B to D. Now let me just copy this out. We need to prove that this vector O to A, which we already know is A, is parallel to B to D. So B to D is this vector here. And we can see, look, that does look like it's parallel to this. Now, before we work out exactly how we show they're parallel, it would seem to make sense to actually find what these two vectors are. Now, we already know that O to A is A, so we need to find the vector B to D. So how could we work out B to D? Well, let's think of an appropriate route. We could go around this way, but I think it might actually be easier to go this way because we know more of the vectors along this route here. So to get from B to D, we're going to go that way. So we can see initially we've got a minus B. We're then doing an A vector. And then we've got half of whatever A to C is. So half of the vector from A to C. So we need to separately work out what A to C is. Now I'm just going to do it in line here rather than writing it out separately. But A to C, to get from A to C, we could do minus A and then a B plus another B. Now we know that vector is also B because we're told that's the midpoint of here. So that movement from here to here is exactly the same movement as here to here. So it's going to be half of A to C minus A plus 2B. So we had a root within a root there again. So then we need to expand and simplify that. So minus B plus A minus half A, and then half times 2B is plus B. Now can you see that the B's cancel, that the minus B plus B cancel, so we're just left with A minus half A is half A. So that whole vector there was just half A. Now we know that two vectors are parallel if one is a multiple of the other. So for example, if I had vectors A plus 4B and I had the vectors 3A plus 12B, this is a multiple of that, because can you see that I could factorize out the 3 here to get 3 brackets A plus 4B. And look, that's clearly a multiple of this because this is 3 times that. So if they're a multiple of each other, then they're parallel. So parallel vectors are multiples of each other. And that's the magic word you should use, multiple of. And you often need to factorize that number up to show that one is a multiple of the other. So for this here, we can see that BD is half A, whereas O to A, which I was referring to earlier, is just A. So all you would need to write here is just that BD is a multiple of O to A, therefore, that's the sort of therefore symbol. You can just write therefore. They are parallel. Yep. And we're going to use that principle in this last question here, where you have to prove that 3 points form a straight line. So let's look at this last hard one. The midpoint of P to Q is W, so that is halfway between there and there. QX to XR is 2 to 1. We had a similar ratio earlier. PRY is a straight line, PRY, so that's a straight line, and R is a midpoint. So if R is a midpoint, if that's B, that's also B, just like we had earlier on this problem. Prove that WXY, so WXY is a straight line. So this is an EdXL question. So let's just copy it out again. So that was B, this vector. Now we're told that R is a midpoint, so that vector must also be B. And W is the midpoint of P to Q, so if that is a vector A, that vector will also be A. And we're told the ratio of QX to XR is 2 to 1. If I write that ratio on, that's going to be helpful. And we need to prove that WXY is a straight line. So this is apparently a straight line. Now all we need to do is to basically prove that this vector W to X is parallel to W to Y. Because if I show that with 3 other points over here, if I've got 3 points A, B, C, and they form a straight line, then can you see that if the vector from A to B was parallel to the vector from A to C, then this must form a straight line. If they weren't parallel, so let's say you had A, B and C like this clearly doesn't form a straight line. You can see this vector A to B is not parallel to A to C, and that therefore clearly doesn't form a straight line, whereas this does. You could also similarly do A to B and B to C. If that vector was parallel to that vector, then again it would be a straight line. But I find it's easiest to do A to B and A to C, and in this case W to X and W to Y. So we're going to find those 2 vectors and show that they're parallel. Let's find the easier one first, W to Y. Now W to Y, to get from here to here, we can do minus A plus 2B. So that's the easy one. Now we need to find the harder one, W to X, because this is going to involve some fractions of vectors. So to get from W to X, let's go this way around, like that. Yep. So to get from W to X, let's go up here first. So it's going to be A plus, now what fraction of what vector is this? Can you see this is 2/3 of Q to R? So it's exactly like we did this kind of problem over here. So that's going to be A plus 2/3 of, and then we separately work out what Q to R is as a separate root. So Q to R is minus 2A plus B. Let's expand and simplify. That's A, 2/3 times minus 2A. Well, 2/3 times 2 is 4/3. It will be minus 4/3 A. And 2/3 times B is plus 2/3 B. So if we collect like terms, 1A minus 4/3, 1 minus 4/3 is minus 1/3, so we get minus 1/3 A plus 2/3 B. Now I said to show that one of these vectors is a multiple of the other, we should really factorise something out. So can you see that if we factorise the third out of that, we get minus A plus 2B. Now this is a multiple of that. Look, it's this vector here times by a third. So it's just that the W to X is a third of W to Y. That's clearly a multiple. So what we need to write as our conclusion for the final mark is W to X is a multiple of W to Y. Yeah, so those are the magic words. It's a multiple of, and then we can say therefore they're parallel. Now this is quite subtle, but it's possible to have 2 vectors which are parallel but in different places. If that was the case, they don't form a complete straight line. But this does form a straight line, because can you see that this vector here and this vector here start from the same point? So if those 2 vectors have a common point, in this case A, then it must form a complete line that's not cut up into pieces like that. So what we need to say is that W is a common point to both vectors, because W to X, W to Y, they had a common point of W. So we write W is a common point here, and then for any proof question, if the question was say, prove that WXY is a straight line, you should finish by writing, therefore WXY is a straight line. Always do that for any proof question, whether vector or otherwise. So therefore WXY is straight, or is a straight line. And that completes our proof.